Okay, so earlier in this section, we have been converting between polar and rectangular form for complex numbers. Now we're going to see some of the pretty cool uses of polar form, specifically multiplication, division, and exponents and roots. So let's start off with multiplication. Now these formulas for multiplying polar form of complex numbers are on your formula sheet. So complex number formulas, here we go. We've got the multiplication, the division, then we're going to have the exponent and the root formulas. So this tells me that if I want to multiply two complex numbers in polar form, I can just multiply the r values and add the angles. Okay? For division, kind of makes sense, right? Because multiplication and division are very closely related, that we can divide the r's and then subtract the angles. Right? Kind of makes sense. Multiplication, division are inverse operations, so it makes sense that if this is multiplication, that's division. If that's addition, that's subtraction. Right? So let's look at some specific examples. So if I want to multiply these two complex numbers, 8 cis 30 times 2 cis 150, that formula that I gave you says that all we have to do is multiply the r values and then add the angles. So it should just be 8 times 2 and then 30 plus 150. So we just get 16 cis 180. That's the polar form for the answer. Now it might say sometimes to express your answer in rectangular form, in which case you would want to write this out as 16 cosine 180 plus I sine 180 and change it to rectangular form. So let's multiply this one and do just that. Let's write the answer in rectangular form. So we know that if we're going to multiply this from our formula, then we're going to multiply the r's and we're going to add the angles. So we're going to get the 6 times 5, which is 30, and then 120 plus 30 is 150. All right, so we're going to need to find the rectangular form. So let's write out this cis abbreviation into its full thing here of cosine plus I sine. Now, what is the cosine of 150 degrees? Well, 150 is over here in quadrant 2, and it has a 30-degree reference angle. So the cosine of 30 degrees is root 3 over 2, but in quadrant 2, we know that the cosine function is negative in quadrant 2, so it's going to be a negative root 3 over 2. Then the sine of 150, well, the sine of 30 is 1/2, and sine is positive in quadrant 2, so that'll be a positive 1/2. Then, so how do I get from this line to this line? Well, I'm going to distribute that 30. So 30 times this fraction, that 30 over 2 becomes 15. So you get that negative 15 root 3. Then distributing this 30 times 1/2, well, half of 30 is 15, and then that's your I term, your imaginary term. Okay, so let's use the division formula. So if we're going to divide two complex numbers in polar form, our formula says we just need to divide the r's and subtract the angles. All right, so we're going to take 12 divided by 6, we'll get 2, and then we'll subtract that to get 270. So I just made a little note here, that 2 came from 12 over 6, that 270 came from subtracting those angles. Alright, so if I ask you to divide these two complex numbers, now these two are in rectangular form. They are not in polar form. You can tell because the polar form has that CIS thing to it. This one does not have that. So these two are already in rectangular form. Now, if you were going to do this without any kind of polar form, you would need to multiply by the complex conjugate on the top and the bottom of that fraction and simplify it. Instead, let's take the approach of converting the numerator and denominator to polar form. 4i is the same as 0 plus 4i. Now, because that's one of those points that is on one of the axes, that's a pretty easy one to convert to polar form. because we don't have to play a guessing game of what angle is it at. Because it's on one of the axes, boom, 0, 4, we know right there is 90 degrees. So it's just 4 cis 90. For 2 minus 2i, that was a little more work to have to do. We have an x value of 2, a y value of negative 2. It is in quadrant 4. The point 2, negative 2 falls in quadrant 4. So we go through our normal process of x squared plus y squared is r squared. We end up with r's root 8 or 2 root 2. The tangent's y over x. So we get tangent theta is negative 1. Taking the inverse tangent to solve for theta, we get that it's going to be a 45-degree reference angle, and it's got to be either in quadrant 2 or quadrant 4. How do I know that? Because I'm looking at this 1 right here, and I know that the tangent of what gives me 1, that's a 45-degree angle. It's going to have to be in one of the quadrants where the tangent is negative. Those two quadrants are 2 and 4. Which one do I use? Well, this point tells me to use quadrant 4. So it's a 45-degree reference angle in quadrant 4, which makes it 315 degrees. So my original 4i becomes 4 cis 90. 2 minus 2i becomes 2 root 2 cis 315. Now to divide these, I divide the r values and subtract the angles. Dividing 4 divided by 2 root 2, dividing that out gives me 2 over root 2. Right, can you see how that happens? That 2 goes into that 4 twice. And then 90 minus 315 is negative 225. Now if I want to rationalize this 2 over root 2, just because I have a feeling WebAssign's not going to like you leaving that unrationalized. To rationalize it, we are going to have to multiply by root 2 over root 2, which is going to simplify that to just be root 2. Because we're going to get 2 root 2 over 2, and then those 2's will cancel. Okay. So now let's talk about exponents. So this is something called de Moivre's theorem. That is a French name. So de Moivre's theorem tells you how to raise a complex number to a power. Right? So it says that if you have some complex number, the exponent is going to be r to the n cis n theta. Now if you think about it, this is really just an extension. So before I go to example, this is really just an extension of our multiplication formula. Right? So our multiplication formula said that if we multiply two complex numbers, we multiply those r values and we add those theta values. So now imagine that instead of these being two separate complex numbers, that these are the same ones. Because that's what it means to raise something to, a power. It means you're going to, multiply that thing by itself over and over again. So imagine these are the same. Well, now we have r times r, and then we have the same theta. So that would be r squared, and then repeated addition is the same as multiplication. So if I keep doing this, and let's say that I have 4 of those complex numbers, then I'm going to have r multiplied 4 times, and I'm going to have theta added 4 times. So this repeated multiplication of r is exponentiation. Should put a 4 there, not an n. And then that cis, oops, there should be a 2 right there. That repeated addition is the same as multiplication. So that's why. So this is just an extension of our multiplication formula. Okay, so let's use de Moivre's theorem and write our answers in rectangular form. So 2 cis 135 to the 4th power. This formula tells me I can just raise r to that power and then multiply that angle by this number right here. So for this case, my n for the formula is 4. So I get 2 to the 4th cis 540. All right, so where did the 540 come from? The 540 came from multiplying this angle by 4. So 2 to the 4th is 16. Now, this 540, I can write as its coterminal angle of 180. This exact same angle, it's not a reference angle, it's just a coterminal angle. So it's the same angle, just within the 0 to 360 that we're used to. So we get 16 cis 180 if I expand that out. Now, why am I expanding it? Because I asked you to write your answer in rectangular form. The cosine of 180 is -1. The sine of 180 is 0. So then multiplying that stuff out, I get -16 plus 0i, which I don't have to write the 0i. It's just -16. Okay, let's do -1 plus I all to the 7th power. Now for this one, this is when polar form is about to shine. Because you guys, otherwise you got to multiply this thing times itself over and over again, distributing out over and over and over and over and over again 7 times. No thank you. So instead, let's change this complex number to polar form. So we have x is -1, y is 1. We know that that point, -1, 1, is in quadrant 2. So using our little x squared plus y squared is r squared business, we get that r's square root of 2 using this tangent, which this looks very familiar, right? We just did one like this, where we have that 45-degree reference angle in the 2 quadrants where tangent is negative. And it's going to be in quadrant 2. So that 45 reference angle is in quadrant 2, which makes theta be 135 degrees. So this complex number, -1 plus I, let's see if I can kind of accent this, that -1 plus I business as a polar form of a complex number there is square root of 2 cis 135. Now you might be like, gosh, that was a lot of work. Well, it's still less work than multiplying that out 7 times. So now raising this to the 7th power, we have De Moivre's theorem that tells us we're going to take the r value to that exponent of 7, and we're going to multiply the angle times 7. So root 2 to the 7th power is 8 root 2. Now I get that by just, root 2 to the 7th power. I don't know how many, 1, 2, 3, 4, 5, 6, 7. Every 2 of these is 2. So every pair. So I get 8 root 2. Then 135 times 7 is 945. I'm going to find that coterminal angle. So I subtract 360 and I get 8 root 2 cis 225. Now you can see I have a little arrow there of continued. So we're not quite done. Why aren't we done? It feels like we should be done. Well, because I asked you to write your answer in rectangular form. So we still got to convert that to rectangular form. Alright, so 8 root 2 cis 225, if I expand that out. 225 is a 45-degree reference angle in quadrant 3. So the cosine of 45 is root 2 over 2. The cosine in quadrant 3 is negative. The sine of 45 degrees is root 2 over 2. The sine function is also negative in quadrant 3. Then I'm going to distribute that 8 root 2 through there. So if I take that 8 root 2 times negative root 2 over 2, those two multiply to be 2. So I get -8. The square root of 2 times the square root of 2 is 2 over 2 is -8. And then the same thing happens over here. Okay, so any complex number that makes the equation of z to the n equals w true is a complex root of w. Okay? that's just a fancy way of saying that, hey, if we undo that nth root, or sorry, that nth exponent, we're going to get an nth root. Now, there are n distinct nth roots of a complex number. So think of it like the square root. Remember how when we took a square root of something, like if we had x squared equals 16, then we would say that x is plus or minus the square root of 16? That's because this exponent right here, when we go to take that square root, we're going to have two answers. Same thing happens here. We're going to have this many answers when we take an nth root. So we have a theorem that is on your formula sheet. It sounds really awful, but I promise you, once we get to the hang of it, it's going to totally make sense. So let's let this be a complex number. The n distinct nth complex roots are given by this formula. Now, let's just take a second and realize this is really just kind of the opposite of de Moivre's theorem. Okay? De Moivre's theorem said that if you're going to raise a complex number to the nth power, you raise the r to the nth power, right? And then you multiply the angle by n. All right, here's the inverse. Instead of raising r to the nth power, we take the nth root. Instead of multiplying the angle by n, we divide it by n. This stuff right here, this mess, is how we're going to get the other roots. So all we're going to have to really do is find one, and then this little magical formula here is going to help us find the rest. I'm not such a big fan of using this formula over and over again, so I'm going to show you how I kind of shortcut it by really just using that formula and then kind of like this as a secondary formula to just kind of boop, 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 find the rest of them. All right, so I'll show you what I mean, because that may not make a whole lot of sense. Okay, so we're going to find the complex cube roots of 27 cis 90. Now, first thing you need to notice is that we're finding the roots, so we are going to be using this formula. Because it says cube roots, we know that my n is 3. All right, so here's cube, 3 answers. So here's how I'm going to start. Remember how I told you I was going to use this formula, but I was just going to use that first part of it. That nth root of r cis theta over n. So nth root of r cis theta over n. So you kind of see how I'm trying to accent the fact that n is 3. So cube 3. All right, so that gives me cube root of 27, which is just 3. 90 divided by 3 is 30. That's my first answer. How many answers am I going to have? Well, I'm going to have 3 because n is 3. To find the rest of the answers, I'm going to use this part right here. This 2 pi k over n. So we're going to take that 2 pi, which is 360, divided by n. So again, you can see how that one's kind of pink, just like the other. So if I take that 2 pi over n, in this case 3, I get 120. I'm going to find my other answers from just this part right here. I'm going to add 120. So, boop, add 120. There's my second answer. Add 120 again. Boop, there's my third answer. There's my 3 answers. Now, check it out. Look what happens if I accidentally, let's just say you don't know when to stop, all right? So we ended up at 270 degrees. Let's say that you add 120 again. You're going to end up with 390, all right? That's the same thing. That's coterminal to 30 degrees, right? You're back at this answer. So if you keep going too far, you are just going to cycle back through these exact same answers. But you should know when to stop based on n. All right, so we're going to use this formula. And then as a little secondary formula, we're going to take 360 divided by whatever n happens to be, and we're just going to add that number over and over again till we get all of our answers. So there's my 120. There's 120. Okie dokie. Let's find the complex fourth roots of 1. Fourth roots means that n equals 4 in this case. Now, 1 is in rectangular form, right? So 1 plus 0i, that's the same thing as 1. If I convert that to polar form, so one thing I just realized I probably should have written just for clarification. So let's write 1 plus 0i in polar form, and that's going to give me, look, that's the point 1 comma 0, so it's right here on that axis. We know that's 0 degrees, and with an r value of 1, so we have 1 cis 0. Okie dokie. So we get the fourth root of 1, and then 0 divided by 4. So there's my polar form. I took the fourth root, and I divided that by 4. That gives me my first answer. That's my first answer of 4, because fourth roots. I'm going to find the others by taking 360 divided by 4 and just adding it over and over and over again. So 360 over 4 is 90. So boop, I'm going to add 90. Boop, add 90 again. Boop, add 90 again. If you add 90 again, you're back at 360, which is the same as 0. So you know when to stop based on n. n is 4, so 1, 2, 3, 4 answers. So this stuff right here is that 2 pi over n, and the k tells you, hey, you just got to keep on adding it. All right, last one. The complex fifth roots. Now this might be a good opportunity to maybe pause the video and see if you can do this one ahead of me. It's already in polar form, so you can go ahead and just start with that nth root of 32 and then that 300 divided by n. You gonna pause it? No? Just gonna watch? You really should play along. Alright, last chance. Okay. So the fifth root of 32 is 2, because 2 to the fifth is 32. And then 300 divided by 5 is 60. So there's my first answer. Doing the 2 pi, or the 360 divided by 5 is 72. So just going to add 72 degrees as many times as I need to get a total of 5 answers. So there's that 72 degrees over here. I'm going to add 72. There's my second answer. I'm going to add 72. There's my third answer. And I'm just going to keep going. How do you know when to stop? Well, when you get to that many answers, or once you get over 360, now you're coterminal to these other ones. So that's another thing to notice, of to kind of let it tell you when to stop. Alrighty, so that concludes section 10.5.